All right, class, next section, 7.3, using similar right triangles. So remember, with similar triangles, we used a lot of proportions to help us find missing side lengths. So we're going to be doing that today, but we're also going to be looking at some special formulas that can help us with that. So theorem 7.5 states, if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So our original triangle is like this big triangle here, ABC. And we're saying if the altitude is the height of our triangle, that would be this red line. If we have an altitude drawn to the hypotenuse, see AB is our hypotenuse because it is opposite our right angle up there at angle C of the green triangle. Then it's saying that the two triangles formed, so those two smaller ones, are going to be similar to each other and similar to the larger green triangle. So we end up with three different similar triangles. Triangle CBD is similar to ABC, ACD is similar to ABC, and CBD is similar to ACD. So two things we can do, splitting the triangles and splitting the smaller triangles can help when comparing those two smaller triangles. So we split up ACD and CBD. Also, you may want to consider redrawing one of the triangles after splitting them so it's in the same position as the other. So this would be D, here we would have B, and C. So if I redrew that smaller triangle to be in that same position as ACD, that could help me match up my sides as well. But if you're not splitting things up and picking out sides like that, we have this other way, or if it's too difficult to do that, we have these theorems. 7.6 geometric mean theorem, or the altitude theorem. From this theorem, in a right triangle, the altitude from the right angle to the hypotenuse is the geometric mean. Now, we didn't talk about what geometric mean is. You don't really need to know that. But what you need to identify is what this formula is. It says part 1 of hypotenuse over the altitude equals the altitude over part 2 of the hypotenuse. So we talked about this being the altitude. That line that is showing us the height of our triangle. But then what that does is it splits our hypotenuse into two parts. At AD and DB. So those are my two parts of the hypotenuse that we're talking about. So we could say AD maybe is part 1 of the hypotenuse. And we could write in our proportion, whatever the length of AD is, over whatever the length of our altitude is. And then that will be equal to whatever the length of our altitude is over the length of DB. So we're going to circle in our altitude. We know that's our red line. So anytime you're given the altitude, you're probably going to want to use this formula. Or if you need to find what the altitude is, you're going to want to use this formula. Theorem 7.7, the geometric theorem, or geometric mean leg theorem, or you could just say the leg theorem. From this theorem, either leg of the original right triangle is used for the geometric mean. So again, let's look at our triangle. And our formula is hypotenuse over the leg equals leg over part of the hypotenuse touching that leg. So first, identify our hypotenuse, that's AB. That would go right there. And then a leg, we can choose either leg from the original triangle. So the big triangle, either leg. So that's either AC or CB. So if I choose CB, that would be my leg. And that would also be the leg I'm using on the right-hand side as well. So whatever leg you choose, you use that leg in both spots on the proportions. Then part of the hypotenuse touching that leg. So in our previous one, we split up the hypotenuse into two smaller pieces, or the altitude split up the hypotenuse into two smaller pieces. We still have an altitude here cutting into our hypotenuse. So that would be DB right there, would be the part of the hypotenuse that touches that leg. So whatever small part there touches that leg, that would be my part of the hypotenuse touching the leg that I was using. Now let's say in my question, it gave me a value for AD. Say maybe AD was 9, but I didn't have a value for DB. And I didn't have a value for CB. Then I would need to use, but maybe I had a value for AC. Maybe AC was, 6. So then I would need to use AC as my leg. It wouldn't make any sense to use CB because I would have to plug in an X for CB, and then I'd have to plug in a Y for DB, and I've got too many variables there. So you can't just necessarily always pick any leg, but you have to choose the leg that's going to help you out, that's going to make it work. And then it will always be the part of the hypotenuse touching that leg. So with using 6 and 9, then I would use AD as my part of the hypotenuse touching the leg. So you just need to keep that in mind too. Where are the values that are given to you to help you decide which leg or part of hypotenuse touching the leg that you use. So here we're going to write and solve the proportion and write your answer in simplest radical form. So we see X. X is our altitude. That's what we need to find. So if we look back at our altitude theorem, we need part 1 of the hypotenuse, or just one of those parts, over our altitude, which will be equal to our altitude over the other part. So I know my altitude is going to be on the bottom over here, and it's going to be on the top over there. Now, part 1 of the hypotenuse can be either side. It doesn't matter. I'm just starting on the left. So that's going to be my part 1 of the hypotenuse. Then part 2 of the hypotenuse will be my other spot. So I've got 3 over x equals x over 12. Then I just cross multiply and solve for x. So x times x gives me x squared. 3 times 12 gives me 36. And then to solve for x, I need to do the square root of both sides. And the square root of x squared is x. Square root of 36 is 6. So x is 6. That would be my simplest radical form. 36 being a perfect square. All right, next example. We have an altitude of 8. One part of our hypotenuse is x, and the other part is 4. So I can have my altitude. Plugging in my altitudes. I know I'm going to have an altitude on the bottom of one side and on the top of the other. I could actually have it flipped around if I wanted 8 on top on the left. As long as 8 is on the bottom on the right, that's fine. So then my 2 parts, part 1 can be x, part 2 can be 4, and then I need to cross multiply and solve for x. So I get 4x equals 64, divide by 4 to solve for x, and x equals 16. And letter C here, we have our two parts of the hypotenuse, 1 and 4. We don't have anything written down, variable or number, for our altitude, but we do have an x on one of our legs. So we're going to use our other theorem, the leg theorem. So let's look back at the leg theorem real quick. What we do with that. Notice we will use the leg on both sides of the proportion, one on top, one on bottom. We'll have the hypotenuse on top of the leg, and then the leg on top of part of the hypotenuse touching that leg. So our hypotenuse is our entire, we have to remember this is the entire hypotenuse of our original triangle. So that's 1 and 4 together. So our hypotenuse is 5. And that's going to go over our leg, which is x. And that's going to equal our leg, which is x, over the part of the hypotenuse touching that leg, which is 4. 4 is the part of the hypotenuse that touches our side x. So when we cross multiply, we get x squared equals 20. Then when we square root both sides, we're going to need to simplify our radical. So the square root of x squared is going to be equal to the square root of 20. Square root of x squared is just x. And then to simplify the square root of 20, that breaks down to the square root of 4 times the square root of 5. And so we get x equals 2 square root of 5. We need to find the value of the missing variable, or the variable, and write our answer in simplest radical form. So some more examples of these. We need to solve for y in this first one. Y is one of the legs of our original triangle, so we need to use the leg theorem. So I know I'm going to be setting it up, leg on the bottom, and leg on the top. My hypotenuse is given to me as 15. So I can write that in. And then my part of the hypotenuse touching the leg is 4. So I can plug that in. And then I cross multiply, I get y squared equals 15 times 4, which is 60. Find the square root of both sides, and then simplify. So square root of 60 is going to simplify to square root of 4 and square root of 15. 4 is our nice perfect square. Square root of 15 is not a perfect square. So we get y equals 2 square root of 15. No other perfect squares that go into 15. In our next triangles, we have x that we need to solve for. X is our altitude. So we're going to use our altitude theorem. So we'll have x on both sides, one on bottom, one on top. And then we take the parts of the hypotenuse. So part 1 of hypotenuse can be 15. Part 2 of hypotenuse can be 10. So that's part 1 of hypotenuse over the altitude equals altitude over part 2 of the hypotenuse. So we get x squared equals 15 times 10, which is 150. Square root both sides. Square root of 150 is going to break down to square root of 25 and square root of 6. Remember, half of 150 would be 75, and I would look at my perfect square chart until I memorize those and kind of work down dividing to see what's my largest perfect square that divides evenly into it. And we would land on 25. So 25, square root of 25 is 5. And then square root of 6 is simplified. So x equals 5 square root of 6. All right, next we have our x value is one of our legs of the original triangle. So we're going to use the leg theorem. So I know I'll have my x on the bottom of one side of the proportion and on the top of the other. Now my hypotenuse is 16, and my part of the hypotenuse that touches my leg is 5. So I have x squared equals 16 times 5, which is 80. I'll square root both sides. Square root of x squared is just x, and square root of 80, half of 80 is 40, and then work down from there till you get to 16 is the largest perfect square that goes into 80. And 16 goes into 85 times. So we have x equals square root of 16 times the square root of 5. So x equals 4 square root of 5. And then the last example. This one can be a little bit tricky. Because if we just look at our variable k is one of the parts of our hypotenuse. So you may quickly think, oh, I need to do the altitude theorem. That's one part of my hypotenuse. I know what the other part of my hypotenuse is, but we don't know what the altitude is. So we would have too many variables there. And then you might jump to our leg theorem and say, all right, k is a part of the hypotenuse touching the leg, and I can plug in k there. But if you look at it, 4 is the part of the hypotenuse that touches the leg that we know. We know the leg of 10. So where does k come in? So let's look at the leg theorem. We know our leg is 10. So I know I'm going to have that on the bottom of one side and on the top of the other. Remember what the leg theorem is. It's the hypotenuse over the leg. So what would be our hypotenuse in this? Remember, our hypotenuse is both legs together, or that entire hypotenuse or length of that original triangle. So that would be 4 plus k. So that's kind of tricky sometimes to identify, but we're just adding those two things together. 4 plus k. We can do that. And then our part of the hypotenuse that touches that leg is 4. So now when we cross multiply, we have 10 times 10 is 100. And then 4 times 4 plus k. So we get 100 equals 16 plus 4k. Subtract 16 on both sides. Working to get k by itself. Gives me 84 equals 4k. And then divide, last step, divide by 4. So k equals 21. All right, that's it on the 7.3 notes. Make sure you do the homework.